Assalamualaikum and a very good morning. My name is RAUDHAH binti MASZAMANIE, and today I will present our project for operating system entitled Synchronization using Semaphore. To begin, let me share the abstract. This project demonstrates the concept of process synchronization using semaphores through an animated roller coaster simulation. In this simulation, there is only one seat representing the critical section. Each passenger symbolizes a process, and the animation clearly shows how the two fundamental semaphore operations, wait and signal control access. The wait operation ensures that when one process is inside the critical section, no other process can enter. The signal operation releases the seed for the next process to use. Overall, this visual approach makes it easier to understand how semaphores enforce virtual exclusion and guarantee safe execution in an operating system. So for the introduction, in concurrent programming, synchronization is essential to avoid conflicts where multiple processes share resources. A semaphore is shared integer variable that supports two atomic operations, wait, also called P, and signal, also called V. These operations help manage mutual exclusion so that only one process accesses a resource at a time, and also handle condition synchronization. Semaphores are especially important because they prevent race conditions by blocking processes when the resource is not available. In our project, the semaphore concept is demonstrated through rollercoaster simulation. Each process is a passenger waiting to take the ride. When the seat is occupied, the wait operation blocks the next process. Once the ride ends, the signal operation allows the next process to proceed. This makes the blocking behavior and control flow more intuitive and easier to visualize. In a concurrent system, multiple processes might try to access the same resource at the same time. Without synchronization, this can lead to data errors and inconsistent behavior. Although semaphores are a proven solution, the concept can be difficult to grasp from theory alone, where many learners struggle to picture how weight and signal actually work to control process flow. Therefore, there is a clear need for a simple and clear simulation to show how semaphore synchronization operates in practice. Our project addresses this need by offering a visual demonstration through rollercoaster metaphor. So for related work, there's one relevant reference. It's the work by Soren Lawson in 1975 who described the BOS2 operating system. BOS2 used semaphore and extended semaphores to manage synchronization among concurrent process. In this system, execution was organized as multiple cooperating sequential process, and semaphores help avoid deadlock. BOS2 controlled access to limited system resources and supported various jobs and input-output devices. This idea relates closely to our simulation. In both cases, a counting semaphore controls access to a shared critical section, in our case represented by the rollercoaster seat, to ensure mutual exclusion and orderly execution.
For methodology part, to effective convey semaphore synchronization, our group use animation as a visual storytelling approach. This method simplifies abstract operating system concept, making them more accessible for a wide audience. We use Canva, a web-based animation and design tools to create the visual explanation. Canva was selected because of its ease of use, drag and drop interface, and flexibility in design frame-by-frame scene. Each visual element, characters, icons, and background was designed individually to simulate movement. After creating the animation in Canva, we use iMovie for post-production editing. iMovie allows us to adjust timing, add transition, subtitle, and background audio to make the video more engaging and informative. This combination of Canva and iMovie provided a streamlined workflow without requiring advanced programming skills. For task distribution, our group divided tasks to ensure efficiency. CHUN focused on the lecturer review, HAZIQ handled report writing, I conducted testing and analysis, RAUDHAH designed animation and edited the video.
So I will show you the simulation flow in the animation. Hello, we're Group 5, Pak GEMBUS. Today, let's learn semaphores with one-seat rollercoaster metaphor. Imagine a roller coaster, but with only one seat. One person rides at a time while others wait in line. How do we make sure it's fair and safe? We use a binary semaphore to manage this. We start with seat 1, meaning the seat is available. There's a queue of people waiting to ride the one-seat roller coaster. To manage who gets right, we use a semaphore. Passenger A walks up and wants to ride. They check the seat using the wait seat operation. Since the seat equals 1, A is allowed to continue, and the semaphore is decremented. Now that A has claimed the seat, they begin the ride. Other passengers must wait until A finishes and the seat is released. Passenger B walks up and also calls wait seat, but since the seat is taken, seat 0 and B is blocked. They must wait until A finishes the ride and the seat is released. Now that the seat is available again, B's blocked wait seat resumes and B takes the seat and the ride starts again. And just like that, the ride continues. Every time the seat becomes available, the next waiting passenger is allowed to board. The semaphore keeps everything safe and synchronized. A binary semaphore ensures only one rider is on the roller coaster at a time, preventing chaos and keeping the queue fair. It's like a traffic light for your code. Thank you so much for watching. That's all from us.
Alright, so I'm Anchue and I'm going to present and discuss about the result and the discussion. So for the first one, the animation interface overview. Our animation was designed with a simple, clear interface. The roller coaster seats represent the critical section, which is when the seat is available, it will indicate 1, and when it's occupied with the passenger, it will indicate 0. And it is also labeled the characters show each track progress. For example, the passenger will be labeled as track 1 and track 2 in the waiting queue. Lastly, the scene also follows the logical sequence of wait, ride, and signal with the caption and the narration guiding viewer through each step. Next is for the output analysis. The animation demonstrates the key semaphore concept, which is F3 3 point, which is mutual exclusion, blocking, and release. So in the mutual exclusion, only one thread accesses the seat at a time. For the blocking, other thread will wait in the queue. And the last, for the release, the signal seat, which means it will freeze the resource for the next thread. Those principles I mentioned are consistently shown throughout the video. Next, it will be the discussion. The discussion, right now, we will give a clear conceptual demonstration which using the animation allow us to illustrate the semaphore behavior step by step, unlike the real-time code which can be harder to follow them. The roller coaster example made the concept, it is relatable to our real world, more easier for the user, for everyone to understand. The label threads and visible cues clarify the process. The feedback from the peers confirm that the visual approach improves the understanding compared to the static textbook diagram. Although not a replacement for coding practice, this method is highly effective for our learning the basics of process synchronization. Right, for the next is the future world. I'm going to pass to HAZIQ to present. That's all for my discussion part.
Okay, my name is HAZIQ. Now I'm going to continue. For my part, 8.1 future work. There are several ways this project could be expanded. For example, we could create a real-time graphical simulation using Kinter or Pygame to show threads moving dynamically. We could also include multiple resources with counting semaphores or demonstrate priority-based access. Another extension could be a deadlock scenario to teach about the risk of improper synchronization. Finally, Applying semaphore logic to other real-world cases like hospital beds or banking systems would make the simulation even more practical. This project successfully illustrated semaphore synchronization through a binary semaphore controlling access to a shared resource. Our simulation showed how weight and signal maintain mutual exclusion, prevent race condition, and ensure safe process execution. The project meets the learning goals of the operating system course and provides a strong foundation for exploring more advanced topics like deadlocks and monitors. This is the reference that we use for this project. And lastly, thank you for watching our presentation. We hope this simulation has made semaphore synchronization clearer and more approachable. We would like to express our sincere appreciation to Dr. Muhammad Zafran for his support and guidance throughout this project. Thank you.